Hello there and welcome back. We are on to our next lesson on thermodynamics. For this lesson, we're going to be talking about heat engines and heat pumps. And just before we start that, I just want to draw your attention to the diagrams I've drawn on the top of the screen here, the PV diagrams. Last lesson, we learned that there are 4 different processes. So isobaric, isovolumetric, isothermal, and adiabatic. And what I want you to do is, before we move on, just take a look at those 4 processes and make sure you know which one is which. And also what is happening to the work in those cases, to the heat in those cases, and kind of how they behave. Because we're going to use these processes, those 4 processes, and we're going to put them together and talk about heat engines and heat pumps. And so you're going to want to understand those processes. And so a heat engine it's any machine that has heat flowing through it. So it takes in heat and then it uses that heat to do some amount of useful work. A classic example of that might be like a locomotive engine, right? Like a steam engine. And so clearly we are pumping heat through it because we have to burn a bunch of coal to heat up the water into steam. And then we use that heat that flows through to do work. Notice also that the heat engine has an exhaust. So heat flows in and then also the steam is released at the end once the work that it can do is done. Now an ideal heat engine follows a reversible cycle. And so what we mean by that is, if we talk about an ideal heat engine, that each of the steps that go through, as we go through the heat engine, could be carried out forwards or backwards with no loss of energy, right? So you could do an isobaric, expansion, and then you could, in theory, contract it right back, and you go right back to where you were with no loss of heat or work or anything like that. Now, of course, real-world engines are messier than that, and they're never going to be ideal, but it is still useful for us to think about these things and model them as ideal engines so that we can better understand the more complex engines that we use. Okay, so here's an example. I've got the first example right here. It says an ideal gas contained in a piston goes through the cycle shown from A to B to C to A. Okay, so we've got our little heat engine, and as we talked about last day, any closed loop on a PV diagram is going to represent a reversible heat engine or heat pump, as we'll talk about in a second. So it tells us that as we go from A to B to C back to A, 1,000 joules of heat flows into the gas in process AB. So we know that heat is flowing into this process AB, and that makes sense because you can see that this is an isovolumetric process where we increase the pressure, but we haven't changed the volume, and so we must also be increasing the temperature, and so heat must be flowing in. So since we're going from A to B, we could think about the change in internal energy, our first law of thermodynamics, as being the heat that flows plus the work that's done. But recognize that this process AB, as we go along here, the volume is not changing. Remember that work is negative P delta V. And again, remember that we define it as negative P delta V because we talk about work being done on the gas. So if the gas expands, then work is done by the gas, and if the gas contracts, then work is done on the gas. But there is no change in volume, and therefore there is no work being done. So the change in internal energy is just equal to the heat, which we were just told equals 1,000 joules. So 1,000 joules flows in, increases the temperature, increases the pressure, but doesn't do any work in the process. So how much work is done in process CA? Okay, so we want to find the process done the work done in process CA. Well, I know that work is negative P delta V, and so you can see that process CA is an isobaric compression. So we're staying at a constant pressure and we're changing the volume, we're decreasing the volume. So I can use this formula in this case because it's just going to be the pressure, which is 2,000 times the change in volume. So a final minus initial, so 0.5 minus 1.0. Now notice that when I do the math here and I calculate this all through, I end up with 1,000 joules of work, and I end up with a positive number, and that makes sense because work was done on the gas in this step because it was compressed. So my work should end up being a positive number, and lo and behold it is. So now what's the total amount of work done and heat used by the process ABCA. So when I do a complete cycle from A to B to C back to A, how much heat must have flowed in, and how much work was done by the engine. Now, there's more than one way to do this, and I'm going to show one way to kind of reason it out. We've already found the work done in process CA. And we know that no work is done in process AB. So I could just say, okay, what's the work done? What's the work done in process BC? Right? That's my last step to figure out. Well, the work done in process BC is really just going to be the area below the curve as I move from B to C. Okay. Now, notice that as I go from B to C, I'm expanding, so I'm expecting a negative answer. And it absolutely is. The area is going to be negative in this case. So I've got a triangle plus a rectangle underneath. So the area of the triangle that kind of sits on the top of this is negative 1/2. My base is 0.5 and my height is 2,000. And then in addition to that, there's like a little rectangle underneath that. So I'm also going to include that. Negative 0.5 times, again, I've got a height of 2,000. And the total work done in this process ends up being negative 1,500 joules of work as I go from B to C. So if we want to think about the total work done, well, I'm just going to think about the work done in each step along the way. So that would be the work done in step AB plus the work done in step BC plus the work done in step CA, and that brings me back together. So if I have all these little steps and each one of them has a certain amount of work, I can find the total done by adding them all up. Well, the work done in AB, we already saw that that is 0. And so the work done in BC is negative 1,500 plus the work done in CA, which we found was 1,000. And so at the end of the day, the total work done is negative 500 joules. And again, I'm not surprised that the total work done is negative because this is a heat engine. This thing is, the gas is doing work for us. And so I get a negative amount of work. Okay, but what about my heat? So the heat that I could find, well, I know my change in internal energy, ABCA, is going to equal the heat that flows through ABCA plus the work done in process ABCA. That's a lot. But recognize that I start at A and I go through the complete process and I end up back at A. So the internal energy at A has to be the same as the internal energy also at A, which means my total change in internal energy must be 0, which is basically just a way of saying that the heat that flows in this case is just the negative of the work, which is negative of negative 500, which is positive 500. So again, this is a heat engine. This makes sense because this tells us that 500 joules, a net amount of heat, a net amount of 500 joules flowed into the engine, and a net amount of work in the amount of negative 500 was done by the engine. Now, if you haven't noticed yet, there is a simpler way to do this, and maybe you've noticed it already. This step here with the work, we can look at each individual step along the way, and sometimes that's useful, and that's why I wanted you to see this process. But if I just want to know the net amount of work done by the heat engine, then I can just find the net amount of area, which is the enclosed area. So right here, the net work is what I'm just going to call the net area. And so we know that that would just be 1/2 base times height. We have to be a little careful here and think about the sign for our work. And because it's a heat engine, because it is doing work for us, because the engine goes in a clockwise fashion, or the cycle goes in a clockwise fashion, then the work is going to be negative. But you can see here that if I take negative 1/2 base times height, 0.5 times my 2,000, I end up with negative 500 joules, which is what I found out doing it the long way around too. So I can look at individual steps, or I can look at entire cycles, or I can look at just part of a cycle. It all depends on what's going to be useful for me for figuring out the problem, okay? So we'll do a couple more examples here. An ideal gas undergoes a process, X, Y, Z, and back to X. And it tells us that the process ZX is isothermal. So this process from here to here is isothermal. You might notice the other processes, XY, well, that's going to be isobaric because it stays at a constant pressure, and YZ is isovolumetric because it stays at a constant volume. Okay, so basically we want to compare the pressure at point 1. So how does this pressure compare to that pressure there? All right. Now notice that we got at point Z, I'm sitting at pressure 2, and at point X, I'm sitting at pressure 1. And I know that this whole thing is isothermal. So this is gonna, I want to remind you of our ideal gas law, which says that PV equals nRT. Okay. And so let's just think about this for a second. We know that that the temperature at Z has to equal the temperature at X because it's isothermal. They told us that from the beginning. So if the temperature at Z equals the temperature at X, I could rewrite this equation here, solve it for T, and set them equal. It would look something like this. I would have something like PZ VZ over NR has to equal PX VX over NR. And right away, hopefully you notice that this simplifies a little bit because my N and R are going to cancel out of each side. And so life gets a little bit simpler. Basically, PZVZ has to equal PXVX. Well, this just comes from one of our ideal gas laws. Really, this is just saying that if the temperature is constant, then pressure and volume can change, but they just have to change with the inverse of each other. Now, at pressure, the pressure at Z, I know that that is P2. So I'm going to call that P2. And yes, my 2 looks a lot like a Z, but just bear with me. But it's sitting at a volume where the volume of Z is 1/2 of V1. Now, the pressure at point X would equal P1. I can see that from my graph. And the volume is V1. So I want to write P1 in terms of P2, and you can see here that the volume is going to cancel, and I'm going to end up with P1 is equal to 1/2 of P2. And this again should sort of make sense because we saw that we went from Z to X without changing the temperature, and we also saw that the volume must have doubled. Well, if the temperature doesn't change and the volume doubles, it makes sense that the pressure must have dropped by 1/2. Okay, so then same kind of idea, just talking proportionally. How does the temperature at Y compare to the temperature at X? So now I want to kind of compare these 2 points. These 2 points right here. How does the temperature here at X compare to the temperature at Y? Well, hopefully intuitively you already have a little bit of a sense that as I go from X to Y, you could see that Y sits on a different isotherm from X, one that's closer to the origin. And so Y, it makes sense, will be at a lower temperature, okay? So we're dropping our temperature, and hopefully you can kind of reason through that. But they're asking for a proportionality thing, so they want to know by how much. So to compare the temperature at Y to the temperature at X, again, we're going to go back to our ideal gas law. So I'm going to start with this. I'm going to say that PY VY equals nRTY. Okay. Now, that's my ideal gas law for my point at Y. I'm going to do something kind of funny here, or maybe it seems funny. I'm going to divide both sides of that equation by the same thing. But what I'm going to divide it by is my formula for X. So I'm going to say PX VX, and this divide this side by nRTX. Now that might seem like a strange thing to do, but recognize that since those are both equations, I can divide them by each other, and I don't break any rules here because I'm dividing both sides of my equation by the same thing. Now, PY and PX are the same pressure. They're both sitting at P1. So these are going to cancel out. And of course, the N's cancel out and the R's cancel out. And what I'm left with is a statement that, a ratio that says that Vy over Vx equals Ty over Tx. And again, this is just another one of my ideal gas laws that we saw previously, which just says, look, if the pressure is constant, then the ratio of the volume change is going to be the same as the ratio of the temperature change, right? That volume is directly proportional to temperature when pressure stays constant. That ratio is basically saying that same thing. So I'm going to solve for either temperature. Let's just say we solve for Ty. So Ty is going to equal Tx times Vy over Vx. And again, I know what those are equal to. So that's going to equal Tx times 1/2 V1 over V1. And so these are going to cancel. And I'm left with Ty equals 1/2 of Tx. And so you can see that my intuition was correct, that the temperature at y had to decrease as I move from x to y. Okay, so it's worth stopping for just a second and thinking about, why is it that heat engines work the way they do? Well, part of it is the first law of thermodynamics, which says that the change in internal energy in the gas is just the sum of the work and the heat done, essentially conservation of energy. But there's a second law of thermodynamics, and there are a few different ways we can state that. But one way to think about the second law of thermodynamics is that heat does not flow spontaneously from cold to hot. So if I have two bodies and one is hotter at a higher temperature than the other, I cannot get heat will never, I should say, flow spontaneously from cold to hot. Now, that doesn't mean it's not possible to happen, but it just won't happen spontaneously. Like if you have a boulder on a hill, well, boulders don't spontaneously go to the top of the hill. But if I wanted to, I could put a boulder on top of the hill. I would just have to do a lot of work in the process. So we can get heat to flow from cold to hot. It just takes work. Now, a classic example of this would be your refrigerator, right? At first glance, that seems to break the second law of thermodynamics, because how is it that we can plug in our fridge and then the inside of it becomes colder than its surroundings? Well, that's because we have to do work. We're constantly doing work to pump heat out of the inside of the fridge to the warmer surroundings. And so a heat pump does the exact opposite thing as a heat engine, where it does work to move heat. Whereas the heat engine used the heat to do work, this just runs in reverse, okay? So we've got an example here, and it says, look at this PV diagram. How can you tell at a glance that this is a heat pump and not a heat engine? And so the first thing to recognize is that the cycle is counterclockwise. So just like we saw with heat engines run in cycles that are clockwise. This one runs counterclockwise, so A to B, B to C, and C to A. So what that means is when we're doing work, when work is being done on the gas, you can see the compression from B to C, it's being done at a higher pressure than the expansion of the gas at A to B. And so we are doing a net amount of work on the gas. Okay, and so how much heat does it pump out every time we do a cycle? Well, again, since it's a complete cycle, we know that the total change in internal energy is heat plus work, and that is going to be 0 because it's a complete cycle, A, B, C, back to A. And so the heat that is pumped is just going to be equal to the negative of the work that is done. And as we saw before, the net amount of work done for any closed cycle here is just going to be the area. So the net work, or the total work, is just this area right here, which is 1/2 base times height. So 1/2 times, looks like my base is about 40, and my height looks like it's 200. And so this is about 4,000 joules. Now, recognize that the work here is positive because the cycle is going counterclockwise, and so we are doing a net amount of work on the gas. And so the heat that flows out must be just equal to negative 4,000 joules every time we complete one cycle. All right, so I want to talk just a little bit about heat engines and just another way to visualize them. So we've been talking about what they do, and yes, they basically heat flows through them, and then we use that heat to do work. One of the ways to visualize it is to look at this diagram right here, okay? So in taking advantage of the second law of thermodynamics, basically heat flows from a hot reservoir to a cold reservoir. And along the way, some of that energy is diverted to do work. Okay, now it's important to recognize what's happening here. Heat flows, it wants to go from hot and it wants to go to cold. Okay, if I just let it, then heat would spontaneously flow from hot to cold, then eventually it would end up at the same temperature, and then that would be it. But what I'm plugging in here in the middle, this is the heat engine. And this is some machine that takes advantage of that heat flowing in order to divert some of that energy into work. And so what I want you to recognize is, for a heat engine, it's not just heat flows in and turns into work. Heat flows in, heat flows out, but less heat flows out than flows in. We've captured some of the incoming heat energy and we've converted it into work. So the heat that flows out must be less than what came in the first place. So the efficiency of this process, because no process is going to be 100% efficient, as you might well know. And so the efficiency of the process depends on the difference of these two heats. It depends on the difference between the heat that goes in, which I'll call QT, the heat from the hot reservoir, and the heat that goes out, which I'll call QC, for the heat that flows into the cold reservoir. So we could say, okay, what is the efficiency of my machine? Which is to say, what percentage of available energy gets turned into useful work? Okay, so that's how I'm going to think about my efficiency. So the work that is done by the machine divided by QH. Remember, QH is the total amount of heat that is available to potentially do some amount of work, and then W is the work that is actually done. Well, again, from this diagram, what you might recognize is the amount of work that's actually done is really just the difference between the heat that flows in, QH, minus QC. So the work that's diverted is just the difference. And I'm going to divide this whole thing by QH. And then because it's an efficiency, you can leave it as a decimal, or you can multiply it by 100% to write it as a percentage. That part's up to you. So when thinking about the efficiency of heat engines, one thing we can do is picture something called the Carnot cycle. Now, the Carnot cycle, I have to stress this, is not a real heat engine. I mean, it's not real because it's reversible and idealized and all those things. But even for an ideal heat engine, this thing just sort of couldn't exist. I'll explain why in a second. So basically, this diagram right here is showing a Carnot cycle, and it goes through 4 reversible processes, okay? So imagine we had a piston, and we started at point A here, and we moved from point A to point B along an isotherm. So what would happen is, first we would allow the gas to expand under an isothermal condition. So we have an isothermal expansion. And then we go through a process B to C, which is an adiabatic expansion. Okay, and then we go from C to D, which is an isothermal compression. And finally D back to A, which is an adiabatic compression. Now, because BC and DA are both adiabatic, then the only time heat flows is during process AB and process CD. Okay, and so what this is this is like the ideal situation for a heat engine. Okay, for a heat engine to use as much energy as possible when heat's flowing in and capture as much of that as possible before it has to exhaust it. And so the key here is, since heat only flows through process A, B, and C, D, then the heat that flows is proportional to the temperature of those isotherms. So heat's flowing in this step here, and it's flowing in that step right there. And so I could say that the efficiency of the Carnot engine is equal to the temperature of the hot minus the temperature of the cold divided by the temperature of the hot. Again, because the heat is proportional to the temperature, because these are isothermal processes. Okay, and so you could rewrite that as you want, as 1 minus TC over TH. Now, I can't stress this enough. This heat engine is like a theoretical ideal maximum. Okay, this would never work as an actual heat engine. Like, just for example, consider process AB. This is our so-called isothermal expansion. Well, when we talked about isothermal processes before, we talked about how for it to be truly isothermal, then it has to expand very, 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 very slowly so the temperature can stay constant. In fact, it would have to expand infinitely slowly. So this heat engine would take an infinite amount of time to do one cycle. The point of the Carnot cycle, again, is just to visualize this is the best, the most efficient a heat engine could possibly be under these conditions. And of course, real heat engines are even less efficient than the Carnot cycle would be. Okay, so let's give an example here. Imagine we've got a nuclear reactor with reactions going on. They're producing steam at a really high pressure and high temperature. So we're producing steam at 310 degrees Celsius, okay? Now this steam is used to spin a turbine and makes a bunch of energy, and then it gets condensed back to water, and then we have to get rid of it, right? We have to exhaust it when it's done, okay? So the water, the steam, is initially at 310 degrees Celsius, and then when it gets exhausted, it's now at 22. And so of course, that water that's exhausted, it still has heat in it. The only way you could have no heat is if you were at 0 degrees Kelvin, absolute zero, and we're clearly not there. So what is the maximum possible efficiency of this nuclear reactor? And that's going to be 1 minus the temperature of the cold divided by the temperature of the hot. Now, at first glance, this might look like it's really, really efficient, right? Because the hot temperature is 310 degrees and the cold temperature is 22. Except we need to recognize that for these temperatures, we have to use them in Kelvin. So the hot temperature is 310 degrees plus 273. And the cold temperature is 22 degrees plus 273. So this is 593, and this is 295. You can see Kelvin. So you can see that there is lots of heat still in that exhausted water that could potentially maybe have been used to do work, but of course wasn't in this case. And there's no way we can access that because heat is not going to flow from cold to hot. So as part of the exhaust, it's just heat that we have to get rid of and never actually use. So plugging this in here, I get 1 minus 295 divided by 593, and this ends up being about 49% efficient, which means that under these conditions, the best that this nuclear reactor could do, the absolute best, would be to use 49% of the heat that flows in and turn that into work. And of course, the actual nuclear reactor is going to be less efficient than that because it's not a perfect machine. So what could we do, potentially, to increase the efficiency of this engine? And this is true for any heat engine. Well, the first thing you could do would be to increase the temperature of the hot reservoir, right? If the heat is coming from a hotter reservoir, then there is more potential heat that you could capture. Or the other possibility is to decrease T cold. If you could somehow dump that exhaust into a colder reservoir, then there would be more heat available in between those 2 points for you to use as work. Okay, that is it for part 1 of heat engines and heat pumps.